Hello. In this video we will take a look at partial fraction expansions of rational functions that are a bit more complex. Our starting point is a rational function f of x, which is given by the ratio of a polynomial in the numerator p of x and a polynomial in the denominator q of x. We will also assume that the rational function is proper, so that the degree of the polynomial in the numerator is less than the degree of the polynomial in the denominator. As such, we can seek a partial fraction expansion involving only linear factors. In other words, f of x is going to be some constant d1 divided by x minus lambda 1 plus d2 over x minus lambda 2 plus all the way to dn over x minus lambda n, where lambda 1 to lambda n are the n roots of q of x. If the coefficients of the polynomial in the numerator and the coefficients of the polynomial in the denominator are all real, then we can show that any complex root of q of x will always occur with its conjugate pair. Moreover, the partial fraction expansion coefficients corresponding to complex conjugate roots are themselves complex conjugate. In particular, let's say in our partial fraction expansion for f of x, we have a complex root lambda 1. Then, necessarily, in our partial fraction expansion, we will also have a term involving x minus lambda 1 conjugate, and the corresponding coefficient will be d1 conjugate. So in fact, we really only need to compute one of these two coefficients because the other is going to be the conjugate. Let's take a look at an example. We want to determine the partial fraction expansion for the following rational function. Now the quadratic factor here, x squared plus 4x plus 13, has complex roots. X is equal to minus 2 plus or minus 3j. As a result, we can factor x squared plus 4x plus 13 into x plus 2 minus 3j times x plus 2 plus 3j. So our partial fraction expansion for f of x will simply be a over x plus 1 plus b over x plus 2 minus 3j plus c over x plus 2 plus 3j. To determine the coefficients a, b, and c, we can use the Heaviside cover-up method. So in particular, b is going to be f of x times x plus 2 minus 3j, and this is going to be evaluated for x is equal to minus 2 plus 3j. So this is simply 4x squared plus 2x plus 18 divided by x plus 2 times x plus 2 plus 3j, evaluated x is equal to minus 2 plus 3j, and after a bit of complex arithmetic, this simplifies to 4 plus 22j divided by 10. The coefficient c is going to be equal to f of x times x plus 2 plus 3j, and this is going to be evaluated for x is equal to minus 2 minus 3j. So this is 4x squared plus 2x plus 18 divided by x plus 2 times x plus 2 minus 3j, and evaluated x is equal to minus 2 minus 3j. And again, after a bit of complex arithmetic, this simplifies to 4 minus 22j over 10. So you can clearly see that b and c are complex conjugates. And so this is expected because b and c are the corresponding coefficients to the complex conjugate roots. So we really only need to calculate one of them and know that the other one we can get immediately as the conjugate. Sometimes it is easier to combine two partial fraction expansion terms corresponding to complex conjugate roots into a single quadratic factor. Let's take a look at an example. We want to determine the partial fraction expansion for the given rational function. In fact, this is the same rational function as the one that we considered earlier, but in this case, instead of factoring x squared plus 4x plus 13 and using the complex conjugate roots, we're going to keep the quadratic term. So our partial fraction expansion will simply be a over x plus 1 plus, I'm going to keep this quadratic term here in the denominator. So in the numerator, because I have a quadratic term in the denominator, I will require in the numerator a linear polynomial, so bx plus c. To determine the coefficients a, b, and c, I can use the method of clearing fractions. So I simply have to multiply both sides of this equation by q of x. This will give me 4x squared plus 2x plus 18 should be equal to a times x squared plus 4x plus 13 plus bx plus c times x plus 1. Now if I expand out the right hand side and in particular group powers of x, I will have x squared with a plus b with x, I'm going to have 4a plus b plus c, and then in terms of constants, 13a plus c. And so these two sides of the equation have to be equal to each other, so I simply have to equate like powers of x, and that gives me a plus b should be equal to 4, 4a plus b plus c should be equal to 2, and 13a plus c should be equal to 18. And if you solve this system of equations, we'll get a solution where a is equal to 2, b is equal to 2, and c is equal to minus 8. So our partial fraction expansion for f of x then is simply 2 over x plus 1 plus 2x minus 8 over x squared plus 4x plus 13. Finally, let's take a look at what happens when we have a repeated root. The general expansion for our rational function f of x is given by the following form. Now, let's assume that one of our roots, lambda L, has multiplicity r sub L. That means we're going to have r sub L terms in our partial fraction expansion involving the root lambda sub L. In order to determine the different coefficients corresponding to the various terms involving x minus lambda sub L, we can actually take successive derivatives of this equation and evaluate both sides at x is equal to lambda L. This leaves us with a general expression for determining all the different coefficients associated with our repeated root. Let's take a look at an example. We want to determine the partial fraction expansion for the following rational function. And in this case, we have one of the roots, x equal to minus 1, that has multiplicity 3. So we're going to have 3 terms in our partial fraction expansion involving x plus 1. So we write our partial fraction expansion as follows. A over x plus 1 cubed plus b over x plus 1 squared plus c over x plus 1 plus d over x plus 2. Now to determine the coefficient d, we can actually use the Heaviside cover-up technique. So d is going to be f of x times x plus 2, and we evaluate this for x is equal to minus 2. So this is 4x cubed plus 16x squared plus 23x plus 13, all divided by x plus 1 cubed, and this is evaluated for x is equal to minus 2. If we plug in the numbers, this will give us d is equal to 1. We can also use the Heaviside cover-up method to determine the coefficient a. In this case, let's consider multiplying both sides of the equation by x plus 1 cubed. So we have f of x times x plus 1 cubed will be equal to a plus b times x plus 1 plus c times x plus 1 squared plus d times x plus 1 cubed over x plus 2. Now if I evaluate this both sides of the equation at x is equal to minus 1, I'll see that this term will fall out to 0, this term falls out to 0, and this term falls out to 0. And so I'm left with a is equal to f of x times x plus 1 cubed, evaluated for x is equal to minus 1, so this is simply going to be 4x cubed plus 16x squared plus 23x plus 13 over x plus 2, all evaluated at x equal to minus 1, and if I plug in the numbers, this will give me a is equal to 2. Now let's take a look at how we calculate the remaining coefficients. So again, I'm going to start with f of x times x plus 1 cubed is going to be equal to a plus b times x plus 1 plus c times x plus 1 squared plus d times x plus 1 cubed over x plus 2. Again, if I simply evaluate both sides of this equation at x is equal to minus 1, I'll be able to determine a. So let me differentiate both sides of the equation. So I take d by dx of f of x times x plus 1 cubed. This is going to give me b plus 2 times c times x plus 1 plus d times the derivative of x plus 1 cubed over x plus 2. Now, if I evaluate both sides of this equation at x is equal to minus 1, this term is going to drop out, and this term is going to drop out. So I can see that b is going to be equal to the derivative of f of x times x plus 1 cubed evaluated at x is equal to minus 1. So this is going to be equal to 8x cubed plus 40x squared plus 64x plus 33 divided by x plus 2 all squared, and this is again evaluated at x is equal to minus 1, and plug in the number, this gives me b is equal to 1. So again I'm going to take as my starting point d by dx of f of x times x plus 1 cubed. And so this is going to be b plus 2 times c x plus 1 plus d times the derivative of x plus 1 cubed over x plus 2. Now again, if I evaluate both sides of this equation at x is equal to minus 1, I will get the coefficient b. So let me now take the second derivative of f of x times x plus 1 cubed, or the derivative of the above equation. So on this right-hand side, I'm now going to get simply 2 times c plus d times the second derivative of x plus 1 cubed over x plus 2. Now if I evaluate both sides of this equation at x is equal to minus 1, again I'm going to see that this term is going to drop out. So this gives me c is going to be 1/2 d2 by dx squared of f of x times x plus 1 all cubed evaluated at x is equal to minus 1. And so this is going to be 8x to the 4 plus 64x cubed plus 192x squared plus 254x plus 124 all divided by x plus 2 all cubed, and I evaluate this for x is equal to minus 1, and when I do that, this gives me c is equal to 6. So my partial fraction coefficients are then all determined using this approach. And so you can see how I can get the coefficients corresponding to the repeated roots c, b, and a, essentially using the expression given up over here. If you have any questions, please send me an email.